This is the video for pre-lecture 8. So we're going to be introducing our final time marching scheme that we'll be discussing in this class. There are certainly many other schemes out there, but we're going to be just focusing on the Euler's method, the Runge-Kutta schemes, and then finally today the Crank-Nicolson approach. So the explicit and implicit Euler's method were examples of a first step, first order method. The Crank-Nicolson, we can sort of think about, is the average of these two approaches. So if we were to consider only our dx dt value evaluated at time index n, that would be our explicit Euler. If we were to evaluate only our dx dt at time index n plus 1, that would be our implicit Euler. But if we take the average of these two slope approximations, here we're dividing by that delta t by 2, taking the average of those two slope approximations gives us the Crank-Nicolson approach. So graphically, we have our plot here in black. This is our x of t. So at our current time, our current state, time index n, we have our slope approximation dx dt at time index n. At our n plus 1 state up here, we can get our approximation for our dx dt at n plus 1. Now this is a unique case where I've got exactly the correct value, so I can get my correct slope there as well. And then what I do is I take the average of these two values. That's our green slope. And so this would be dx dt at time index n plus dx dt at time index n plus 1, and then we're just sort of averaging those two values together. Okay? So, despite us using an explicit and implicit scheme, because we have our n plus 1 values contained in this approximation of our dx dt, our method is still going to be implicit. It's still going to require us to rearrange the equation so that we can isolate our xn plus 1 terms on the left-hand side. Let's go ahead and take a look at an example of this. Simple example, dx dt is equal to t minus x. Our initial condition is x at t equals 0 is equal to 0. We're going to take two time steps with a value of delta t is equal to a half. So let's start by simply writing our equation. So that would be x of n plus 1 is equal to x sub n plus delta t by 2 times our dx dt evaluated at time index n, so that's going to be t at time index n minus x at time index n plus our dx dt evaluated at time index n plus 1, so that's going to be t at n plus 1 minus x at n plus 1. Okay, we have an x of n plus 1 term here, and an x of n plus 1 term here. We're going to move the one on the right-hand side to the left-hand side. That's going to give us 1 from our term on the left-hand side, plus delta t by 2 from our term on the right-hand side, times x of n plus 1 is equal to x of n, plus delta t by 2 times t of n minus x of n plus t of n plus 1. Can divide across to give us x of n plus 1 is equal to x of n plus delta t by 2 times t of n minus x of n plus t of n plus 1. All of that divided by 1 plus delta t by 2. So that's our rearranged equation. That's what we'll use to perform our two time steps. So at t of n equals to 0, our x of n value is also equal to 0, and our t of n plus 1 value is going to be equal to 1/2, as is our delta t value. So you can take those four values, plug them into our equation, and say that, okay, x of n plus 1 is equal to x of n, which is 0, plus delta t by 2, which is then 1/4, times t of n, which is 0, minus x of n, which is 0, plus t of n plus 1, which is 1/2, all divided by 1 plus delta t by 2, which is 1/4. That's going to give us, on the top, we will have a 1/8. And at the bottom, we'll have a 5/4. And that reduces to 1/10. Okay, so then our next step is then, okay, t of n is now equal to 1/2. Our x of n is equal to 1/10. And our t of n plus 1 is equal to 1. So our x of n plus 1 is equal to, now x of n is not 0, but it is 1/10. Plus delta t by 2 is still 1/4 times t of n, which is now 1/2, minus x of n, which is 1/10, plus t of n plus 1, which is 1, all divided by 1 plus delta t by 2, which is 1/4. This all reduces to a value of 9/25, or 0.36. Analytically, our value is 0.368. So we're accurate to within a couple percent. Well, so this is for a relatively simple ODE, where rearranging and isolating the x of n plus 1 value is somewhat complicated, but not too difficult. What if we start to deal with a more complicated system, where it's not straightforward to isolate our x of n plus 1 value? We need to come up with an alternative approach that doesn't rely on us to be able to manipulate our equation to isolate that x of n plus 1 term. One approach to doing this is what's called the predictor-corrector method. So the predictor-corrector method is a way that we can address implicit methods without requiring the manipulation of the n plus 1 terms, because sometimes this is not possible. So what we do is we start by guessing the value of an x of n plus 1 approximate value, use that to estimate our dx dt of n plus 1, and use that to give us an estimate for what x of n plus 1 is. And then we would use this new estimate to give us a better approximation of what dx dt is over and over and over again. So let's go ahead and work this out through the example a little bit. So we know that initially x of n is equal to 0, and t of n was still equal to 0, and t of n plus 1 was equal to 1/2. What we didn't know was what x of n plus 1 was. And if we did know that value, then we could use our base equation, which was x of n plus 1 was equal to x of n plus delta t by 2 times tn minus xn plus tn plus 1 minus xn plus 1. So that was our base equation. And well, if we knew x of n plus 1, then what are we even doing this for? We would then know the left-hand side. But what we're going to do is we're going to say, okay, well, what if we're only approximating the value on the right-hand side? So what if we call this our first guess of what x of n plus 1 was? Well, if we have a first guess for x of n plus 1, that's going to give us maybe our second guess for x of n plus 1. And then we could use that second guess to give us a third guess and see if we converge towards a value. Well, a natural place to start for time marching schemes is to assume that our time step is small. So we start by guessing x of n plus 1, our first guess, is just simply equal to x of n. So we'll start by guessing a value of 0. Well, let's see how this does. Well, plugging in, our x of n value is 0. In fact, let's do this in black because some of these things won't change. So our x of n value is 0, our delta t by 2 value is 1/4, our tn is 0, our xn is 0, our tn plus 1 is 1/2. Now we have the only thing that might be changing as we take more iterations, and we're going to set that initial value to be 0. Okay? Well, plugging all that in, that gives us a value of 1/8, or a value of 0.125. Which actually isn't too bad, because what we know is that the analytic solution says that x of n plus 1 was equal to 1/10. Well, let's see what happens if we take another approximation. So now we say, okay, x of n plus 1, and we're going to just say, okay, this is approximation 3. Is equal to x sub n, which is still equal to 0, plus delta t by 2, which is still 1/4, plus tn, which is still 0, minus xn, which is still 0, plus tn plus 1, which is still a half, minus the new x of n plus 1 value, which is now not 0, but 1/8. Well, what does that give us? That gives us a value of 3 over 32. Which is remarkably close to 1/10. And if we were to repeat this, we would get values of 0.10156, and then x of n plus 1 value of 0.0996. And so what we can see is that as we take more and more iterations, plugging those values in, we approach the expected value of 1 divided by 10. Okay? Now, if we were to take a time step forward, we would then have to say, okay, well, at some point we have to stop. And so we would make the assumption, well, once we see changes of the value of x less than a certain value, that would be a tolerance, then we can assume we're close enough that we can time step forward. So then we move on to the next time step where we say, okay, well, now t of n is equal to a half. Our x of n plus, or x of n value is whatever our final guess was, so maybe it's that 0.0996. Our t of n plus 1 is now 1. And our x of n plus 1 value for our first guess is going to be that x of n value that we start with, so 0.0996. Then we can take all this stuff, plug it in to give us an x of n plus 1 second guess, and a third guess, so on and so forth, until we reach convergence. And then we could take this on down the line. Now, the one thing I would say is ultimately, though, this method is still limited in the sense that there's still truncation error. And what we got previously for this example, this value of 0.36 after 2 steps is the best that we could hope for in terms of approximating our true value here without changing our time step. Okay.